All right, everybody. Welcome back to your favorite class, obviously. Okay. Hopefully, we can all hear me in the online world. Please let me know in the chat if you can hear me. Otherwise, I'll have to amend some things, but I think all should be good. Just a reminder, kind of where we left off. We were sort of introducing and talking about combined loading. Went through kind of the equations that we talked about for combined loading, what you might see for normal stress and shear stress. We talked about method of superposition. So what I kind of like to do is maybe just do a quick recap, 3 to 5 minutes. So we kind of recap what we did last lecture, and then we'll move on today with looking at some of the analysis techniques and actually doing some example problems. So I get some comments here in the chat from the Peanut Gallery. The audio isn't that great. Uh-oh. How about now? Is that better? Let me see if I can adjust the device settings here. How are we doing? Is that better? I sort of brought it a little bit closer. Is it just muffled? Is it too loud? Answer me! I think there's actually a delay between. Yeah, Joe says it's good, so I think we're good. All right, let's go ahead and get back to it. So I'll share my screen here now for those people that are in Teams. You'll just have to talk a little bit louder. And then those of you in class should be able to see what's on the board behind me. Okay, so let's do a quick review of kind of where we were last time and what we did last time. Let's recap here with combined loading. All right, we said that loads and forces and moments on a structure can create both normal and shear stresses. So normal and shear stress from loads, moments. Okay, and we talked about normal stress coming from axial loading or bending. And so normal stress here, we typically use the equation or the symbol for normal stress, which is sigma. It's a combination of axial loading and whatever normal stress might come from bending. Right? If we expand these equations out, it would be sort of the summation of all of the forces that might contribute to axial loading. So the summation of kind of this first equation that you learned in your 2004 class, which is F over A or P over A, the axial load divided by the cross-sectional area, plus the summations of what you might get from bending a particular cross-section, which would be plus the summation of my over I, or sometimes seen as negative my over I. We'll talk about directionality a little bit more later in the class. And so these summations would indicate that you are looking at each one of these individual forces and moments separately, and then adding up all of their contributions to determine what the total normal stress is at some particular point in your piece. And the shear stress, similar kind of concept, in that we may have loads and, in this case, torques, which are contributing to the total amount of shear stress in the piece, and that's going to be shear stress that comes from transverse loads and shear stress that might come from torsion. All right, so if we expand that out a little bit, the shear stress that we get from transverse loading, usually the equation we see here, is the summation of the contributions of VQ over IT. So it's probably the most difficult of the contributions to stress that we might see. That's because we have to calculate the first moment of area, this value Q, which is just generally a little suspicious for some of the students to calculate. And then also, we're going to add to that the contributions of torsion, which is going to be TCJ, where T is the torque, C is the distance from the center of the circular member, and J is the polar moment of inertia. All right, so there we go with our normal and shear stresses. And we said that we could sort of sum the contributions of these individual elements, the loads, the torques, using what's known as the method of superposition. Okay, so that's adding each individual contribution by sort of looking at it on its own, and then giving us a full total sum. So your ability to add contributions of stresses from individual loads or moments. Or torques if you have torques, but a torque is technically a moment, so hopefully we're okay with that. All right, and there's some assumptions that underlie the method of superposition when we can or cannot sort of add these individual contributions together. And for this to work, we have to have homogeneous, isotropic, and linear elastic. Okay. How's my volume now that I've been going for about 5 minutes? You let me know in the chat, that would be nice. All right, volume in the room, okay? You guys hear me? Okay, good. Okay. Maybe the handwriting's a little suspicious, but I'm working on it. Okay. All right. What do we say in the chat? Good, says Michael. All right, everyone's good. All right, so with that in mind, let's talk about generally the analysis method. We talked about this a little bit, but I want to just reinforce this. Okay, the analysis method here is we're going to relocate all of our forces and moments appropriately to the point of interest on our structure, and then look at the contributions of each one of those forces and moments to things like shear stress and normal stress. Okay, so we relocate forces and moments to point of interest. Then add contributions to normal and shear stress from each element, each load or moment. Okay. I drew kind of the mechanics potato with all the vectors and the loads on it last time and showed how we're going to relocate our forces to create force couple equivalents and all that sort of stuff. The good stuff you learned in 2001. Yep. So with that in mind, that's kind of the end of our recap. Now let's dive in and actually do some example problems using this general methodology. So if you have the lecture notes with you, I'm going to be doing example problem number 1, which is kind of here. I'm going to pull it up on the screen for everybody to see. Maybe I'll just give you a second to copy what I've got written down if you're still copying that. And then I will get the example problem up here in just a second. Maybe give you 30 seconds or so to copy this down. And then I'll put the example problem up and we'll go through it. Okay, so I'll pull up the slide here so we can all kind of take a look. So here's the first example problem. We've got this solid rod. It kind of looks like maybe like a door handle, like an extended door handle. It's got a radius of 0.75 inches. So this entire thing has a consistent radius even through the bend. If it's subject to a force of 800 pounds at point B, we want to determine the state of stress at point A. So I'll maybe give you 30 seconds or so to copy this down. Everyone make their best Pictionary pictures possible. So A is kind of on the left-hand side of that rod there. If you want to get technical, it's extended 0.75 inches off center in the X direction. Helpful? Let's be precise. Rawr. And that whole lab lecture about precision and being clear and yada yada. Okay. So go ahead and keep copying it down if you are. I'm going to actually translate the picture over to the writing pad so that we can all kind of work from that. And I'll just transfer the relevant information over so we can all sort of still have the picture and the information if you were copying it down. Okay, so I'll bring this in here. This is the picture that we're sort of working with right now. And what we're looking for is we want to find state of stress at point A. Okay, and for clarity, here's point A. And here's point B, where we're kind of applying this 800-pound load. Okay, so as I mentioned in my analysis techniques, the first thing that we want to do is we want to relocate the forces and moments on the structure to our point of interest. Well, kind of our cross-section of interest, or the point of interest on this particular piece that we're interested in, is the point that contains point A. So what we're going to do is we'll sort of make a cut in this rod at point A, and we'll relocate the forces that exist on the structure to that particular location. Okay, so our first step here is we're going to relocate that 800 pounds to the cross-section that contains point A. All right, so I'm going to make a picture here of basically this rod that I've sliced in the cross-section that contains point A. All right, so here's kind of the cross-section that I've sliced through that contains A, and this is kind of going backwards here into the wall. Right. We might give ourselves a coordinate system for this problem, just to be clear, and I'm going to try to mimic the coordinate system that was actually given in the problem itself. So here we have a coordinate system where y is kind of on the axis of the bar, z is upwards, and x is sort of off to the left here. Right. Now on this structure, on the left-hand side is where we have point A. And we're going to relocate that 800-pound force to this particular cross-section. And I want to relocate it to the center of this cross-section. Okay? So we're going to relocate this particular force. And so we'll pick up this force here and just drag it to that cross-section. It's going to retain. So we'll have this 800 pounds that still exists and still points in the same general direction. So here's the center of my cross-section. That force is pointing down. Here's 800 pounds. Right. Now, by sort of the force couple relationships that we know from statics, when I pick up this force and I move it to a new location on the structure, I have to account for the moment that's created when I do that. So we're going to have an equivalent force couple system at this new cross-section, and I'm going to have to do something about the resultant moment that exists when I relocate this force. So my force here is pretty obvious, and again, when I talk about vectors, I'm going to put sort of this dash over the top. So here the force is in vector form, negative 800 pounds, and this is in k hat. Okay, remember, vectors need a magnitude and a direction, so negative 800 pounds in k hat. Now the resultant moment that exists is gotten by your typical statics methods, which is r cross f. So here we have r cross f. This is how we're going to calculate the moment that results in this particular cross-section. So f, that's pretty obvious. This is the force that I just defined at negative 800 pounds in k hat. But now the r is where we kind of have to maybe take a step back. Right? So if I'm doing r cross f, I want to draw a vector from where I am, so this cross-section I've cut, to where that force existed previously. So the r of interest here is this general vector r. And this is the vector that I'm going to use to relocate the equivalent moment to that cross-section of interest. Okay? So to calculate this moment appropriately, we need this value of r. And we can see sort of from this picture here that we're going to go 10 inches in what is the y direction. So it will be 10 in j hat. And then we have to go 14 in the x direction to go from our cross-section of interest to point B. Right? So here I'm going to have this vector r, which is 14 I hat, plus 10 j hat inches. Right. So that means then that the moment that we'll have that results on this particular cross-section will be 14 I hat plus 10 j hat inches crossed with my force, which is negative 800 pounds in k hat. All right. So we execute this math, and we'll get a moment here that is negative 8,000 I hat plus 11,200 j hat inch pounds. All right. So if you need to brush up on cross products, maybe do that on your own time. Hopefully you've had enough engineering class where cross products have been beaten into your brains. All right. So now I have these two moments, one in I hat and one in j hat, that have resulted, and that I can draw now sort of in my picture on the left-hand side. So negative 8,000 in the I hat, all right, well, that's going to be sort of this double arrow in the negative x direction. So that's kind of this guy here, which is 8. I'm going to draw as positive 8,000 since I've sort of drawn it to the negative x direction. And this will be inch pounds. And then I have 11,200 j hat. All right, so in j hat direction, that's here coming out in j hat, is 11,200 pounds. All right. So after relocating that 800 pounds, this is the resulting moment and torque that exist. 8,000 inch pounds and 11,200 inch pounds. So now we kind of have a complete picture of what's going on in the cross-section that contains point A. All right, so now after relocating my forces and moments, I'm actually ready to dive in on the normal and shear stresses. All right, so let's do that. All right, so now let's look at the normal stress at point A. And just for reference, I'm going what I think is excruciatingly slow through this particular example. I know there are ways to calculate the moments in shorter fashion. I know there are sort of ways to get there a little bit more quickly, but this excruciating detail, as I think, is important, at least for this first example. Okay? So now the normal stress at A, we're going to enact the method of superposition. So the method of superposition says that my stress at point A is going to be the summation of the axial contributions, which is this P over A, plus the summation of the bending contributions, this my over I. Or you might see it as negative my over I. We'll talk about directionality in a second. All right. So remember, this is sort of like the axial contribution here. And these are like the bending contributions. So let's go up and investigate our loads on this particular piece. The only actual load that we have that's not a moment is this sort of 800 pounds here. And if I'm concerning myself with axial loads, these are loads that move into and out of the cross-section of interest. So in this particular example, this 800 pounds is like across the face, okay? It's not along the axis of the piece. So that tells me that this 800 pounds is not an axial load, but it's a transverse load, okay? And the transverse loads are going to be responsible for sort of the transverse shear stress component that is not important to us right now when we're talking about normal stress. Okay, so because of that, I don't actually have any axial loads that are acting on this particular member. Okay, so I don't have any loads in sort of this y direction. There are no loads that run along the axis of this member. All right, those don't exist. Okay, so there's no contribution to the normal stress from any axial loads in this particular problem. Now, what about bending? Okay, bending here I will have to consider. So I do have a couple of loads that look like bending loads. Okay. We'll notice here first that this particular double arrow is in the direction of the axis of the beam. And so this here is a torque. And so this will become important when we're talking about sort of the shear stress that arises from torsion. And that's because this arrow is along the axis of that particular member. So the only thing I really have to concern with for myself in this particular problem is this sort of 8,000 inch-pounds that is the bending load that is being put on this particular cross-section. Okay, so here this is a bend contribution, and this guy here is a torque. So let's approach this with the consideration that we're going to have to accommodate the normal stress from bending at point A from that moment. So really the only thing I have to concern myself here with is this my over I term. Right. So the moment that's applied here is 8,000 inch-pounds. We can plug that in straight away. Now this next term here, this y term, is the distance from the neutral axis to the point of interest. In this particular situation, it's not necessarily y, it's actually z. So with this particular bending moment, I'm trying to sort of think about putting my thumb of my right hand along that double arrow and how that curving motion of the rest of my hand is going to act to sort of bend the bar. Okay, so think about bending the bar about this axis of rotation by sticking your thumb in the direction of the double arrow. Right. So what that's going to do is, particularly, it's going to leave us with a situation where we're sort of in tension on this top side, and we're in compression on this bottom side. All right, so if we think about sort of curving this particular guy, that's what's going to happen for this particular piece. Right? And we're sort of compressing the bottom side and pulling this top side. So that means that the neutral axis of bending for this particular applied moment is right across the center of this cross section here. And that's kind of a key point about these bending moments, is that when you have a bending moment in the cross section of your piece, the neutral axis will be along the same line of the double arrow. So here, this is your neutral axis for this 8,000 inch-pound bending moment. Okay. So now let's go back and look at our variable y. All right, remember that this variable y is the distance from the neutral axis to the point of interest. So here, point A on the left-hand side here actually lies right on that neutral axis. So because of that, the contribution to the normal stress from this particular bending load is going to be 0. That's because this variable y here is 0, right? So times 0 over something that's non-zero, meaning that my normal stress that occurs at point A in this particular problem is 0. This is excruciating detail, and I think maybe many of you can just sort of see this already intuitively, but I like sort of showing it very clearly. Okay, so this is the full normal stress at point A for this problem. So we don't have any normal stress at A. Okay, so let's continue then with the shear stress. Right. Again, by method of super principle, it's the summation of what is the transverse shear components plus whatever you're going to get from torsion. In equation form, this is the summation of VQ over IT plus the summation of TC on J. All right, so let's tackle these one at a time. This is your transverse shear component, and in this particular problem, we do have a transverse shear load that's coming across our face. All right, so remember this 800-pound load is kind of coming across our face and providing us with some transverse shear. So we're going to have to account for that. So let's work through that particular piece of this, the 800-pound load. Okay. So this is going to be VQ over IT, this is 800 pounds, multiplied by this variable Q. All right, so now this is where things get a little bit complicated. Remember this Q is the first moment of area. We talked about this. That Q is generally equal to, maybe I'll make this completely sort of a separate thing. Sidebar, Q is y bar prime A prime. This is our general equation, where A prime is the area of interest above the line that is defined by the thickness of the piece at the point of interest. Okay, so when we're looking at this transverse shear component, we're looking specifically at point A. So when I identify this point, I want to draw a line across my member that is sort of perpendicular to the applied load. So at point A, I can draw this line across my piece at the point of interest. And the length of this particular line here is the length that is little t in the equation VQ over IT. Drawing this line allows me to separate this cross-section into two different areas, one above and one below the line. I'll just highlight this area sort of above the cross-section here. Okay. Remember that the area above this cross-section is this A prime variable in the equation Q is A prime y bar prime. So that is this variable here. It's the area above the line defined by little t. Okay. Now the y bar prime, this is the centroid of the area defined by A prime. So here that is the centroid of this green area, which lies right about here. Okay, so here's your y bar prime, that length there. So that length is well known for a half circular area. So the distance from sort of point A vertically to that centroid of the half area is known. And so generally our variable Q here, which is y bar prime A prime, is going to be sort of an equation form. This centroidal location is 4r over 3 pi. I'll look this up sort of in any table. Multiplied by the area that is this circle, which is pi r squared over 2. So here, for simplification's sake, we can sort of whittle this down a little bit. Get rid of a pi, get rid of a pi, reduce this to 2, get rid of that guy. And you're going to end up with 2r squared over 3. So we can now use that in our calculation of the transverse shear stress. So 2r squared on 3. Here will be 2 times 0.75 inches squared on 3. Right. I'm going to now divide this by IT. Remember, I is my area moment of inertia. Here, that's pi r to the 4th. Sorry, pi on 2. R to the 4th, which is 0.75 inches 4th, multiplied by the variable t, which is the length of the line which is moving through the cross section at point A, which is 2 times the radius, which here will be 1.5 inches. Okay, I got a comment here in the chat. Do I mean cubed? Yes, I do mean cubed. Thank you. Appreciate that, Tim. Thanks. All right. And man, I'm rusty. Should be a 4. Pi and 4. All right. Yikes town. All right, so here's my sort of transverse shear component. Here. I'm going to add to this my torsional component, which is TC on J. And I do have one torque here, which is 11,200 inch-pounds, and this is sort of in the positive y direction. This is going to be plus my torque, which is 11,200 inch-pounds. I'll move this over. Multiplied by C, which is the distance from the center of the piece to point A. So this here is my radius, 0.75 inches. Divided by J, which is pi on 2, pi to the 4th, r to the 4th. And this is my torsional component. Now, I got to think about the signs for each one of these as well. I've kind of neglected that up to this point. So let's think about the sign of the transverse shear. Give you a second to copy down what I have. So for the transverse shear, this particular force is coming across the face in sort of this negative direction. So it's coming sort of downwards. So for that reason, we're actually going to have a negative contribution for a transverse shear. Similarly, we're going to have a negative contribution from the torque, and that's because this torque here is tending to sort of spin this rod in this sort of counterclockwise direction, right? It's sort of trying to rotate this rod generally in this direction. That means that at point A, this sort of rotation is going to kind of force me in this downward direction. We're going to talk more about this when we talk about three-dimensional stress at a point, but for now, the contribution to the shear at point A from the torque is going to be in the downward direction, so also a negative contribution. All right. So all said and done here, my contribution from the transverse shear after calculation, 0.60 KSI. My contribution to the shear from the torsion is going to be minus 16.9 KSI. So when all said and done, my shear stress at A is going to be negative 17.5 KSI. All right. So I really kind of beat that one to death. It really went pretty slowly. The full stress state, I don't have any normal stress. My shear stress, negative 17.5 KSI. All right. Let's do one more example and we'll power through it a little bit more quickly this time. And we're going to basically use the same picture, except we're going to analyze a different force that's occurring. kind of have the same idea here. Same rod. But here, the radius is still 0.75 inches. But we have a new force. So we want to kind of go through the same process. Find normal stress at A and shear stress at A with 500-pound bud. This is where I'd take a sip of my coffee if I had any coffee. Okay, so we're going to go through the same procedure, and I'm going to draw a picture again because, pictures are good. So here's my cross-section. I still have at this particular cross-section point A, which is my point of interest. I have my coordinate system again, which I'm going to utilize. Here we have the y direction, z direction, x direction. And I'm going to relocate this 500-pound load here to point A. So I'm going to relocate it to the cross-section containing A. So the first thing you'll notice is that this 500-pound load gets relocated directly, and it's actually in this y direction. So here we have 500 pounds relocated to the cross-section containing point A, the center of the cross-section containing point A. All right, so straight away, my force is going to be 500 pounds, and this is in J hat. Okay. Next, I need my moment, which is again R cross F. The R we calculated before, so this is, I'm just going to simply replicate this. It's going to be 14I plus 10J inches, crossed with my force here, which is 500 pounds, and J hat. My J is a little suspicious. J. There we go. So if you're doing this now, I only have one resulting moment component, and that's because like the J cross J will just go away. So I'm going to end up with 14I crossed with 500J. It's going to get me 7,000 K hat. Positive K hat. So my resulting moment on this cross section will look something like this. My double arrow sort of in K hat and 7,000 in pounds. All right, let's define the contributions to the stress estates from each one of these individual components. So the 500-pound load here, this guy, is going to be what kind of contribution? Your choices are axial, bending, transverse shear, or torsion.
Axial.
Axial. I got it in the earpiece too. Someone said in the chat. Thank you for participating. Yes, this is axial. Thank you. All right. And then this 7,000 inch-pounds. It's not a torque, so this has to be some bending contribution. Yes, participate, get involved. Rawr, even you. Okay. So here is your axial contribution. Here's your bending contribution. All right, so let's power through. If I only have axial and I only have bending, that means there's no transverse shear, there's no torsion. So in this particular example, shear stress at A, which again is a combination of torsion and transverse shear, is going to be 0. I don't have any transverse shear, I don't have any torsion. So that's convenient. The only thing I have to concern myself with is the normal stress at A, which is going to be this P on A term plus the my over I. All right, my axial load here, P, is running sort of in the positive direction. It's tending to sort of pull this bar, so we're kind of in tension. We'll keep this positive value here as 500 pounds. Over the cross-sectional area of the piece, which is pi times the radius of this piece, 0.75 inches squared. And I'm going to add to that the contribution from bending, my over I. I'm going to sort of take a look at my schematic here to show me if I'm going to have like a tension or a compression from this particular bending moment. So if you think about sticking your thumb in the direction of this double arrow and sort of curving the bar around your thumb, you're going to see tension at point A and compression on the opposite side. So here, this particular bending moment, the 7,000 pounds, produces tension here and produces compression here. All right. So because of that, we'll take the positive value for the contribution to the normal stress from bending. And we'll say here that this is going to be plus the 7,000 inch-pounds multiplied by y, which is the distance from the neutral axis of bending to the point of interest. And remember that that neutral axis here is along the double arrow. So the distance y in this particular situation is this distance here, my variable sort of y in this particular equation. And here that's just the radial distance, 0.75 inches. This is going to be over the area moment of inertia, which is pi on 4 times the radius to the fourth, 0.75 inches to the fourth. All right. So in the end, my normal stress, I'm going to have contribution from this axial load of 0.28 KSI. And I'm going to add to that my contribution from the bending moment, which is 21.13 KSI. And I'll have a total normal stress in this sort of new situation with the 500-pound load, which is going to be 21.4 KSI. All right. Hopefully this is ringing some bells. Hopefully you guys, did some of this combined loading when you were in 2004. I know I'm going through it relatively slowly right now, but hopefully it's sort of cementing those ideas in your head. All right, when we come back on Wednesday, we'll finish up combined loading with a more thorough example, and then we'll dive in on three-dimensional states of stress.